I'm going to walk you through the simulation. Hopefully you finished yesterday. If you're pretty confident with your answers and you don't feel like listening and watching this, you can just start watching the videos that have been posted on Synergy. I changed up the order of those a little bit just to make sure that it aligns with what we're doing this week and what we're doing next week. So hopefully you checked it out on Sunday. If not, just make sure you watch it before you begin the assignment that you're supposed to finish tomorrow. It will make things a lot easier on you if you get extra exposure to that material as usual. So looking at our simulation here, number one, I've already went to this link. So we need to press the play button, and then on the left side press the model box. So here we go. Click the model box. Next thing we need to do is press the play button. Oh, I'm sorry. Click the gravity, force, velocity, path, and grid boxes on the right side of the screen. So I need to click all 4 of these. Then I want to press the play button on the bottom and allow the Earth to make it halfway through its orbit. Press pause when the planet gets to the original horizontal grid line on the sun's left side. So what we're going to do is let this Earth go through 1/2 of its orbit. And try to pause it right when it gets to the other line. What's nice about this is you can pause it and then step to where that's at. Okay, so the Earth started at this point, made its way halfway through its orbit, and ended at this point. So what we want to do now is compare the distance the planet was from the center on the right side to the distance from the center on the left side and use the grid lines. So when we look at this distance, here it goes 1, 2 total boxes from where it started to the center. And over here we have 1, almost 2 total boxes. So that means that this isn't quite a semicircle and this total orbit isn't circular. It's a little bit different. When people first, I guess you could say, discovered that it was the Earth revolving around the Sun and not vice versa, we all assumed that it was circular orbits, but turns out it's not quite circular. So we want to use the observation from number 4 to describe the shape of the planet's orbit or any planet's orbit as it travels around a star, or they travel around a star. So we'll use 23 from our pretest for assistance. I don't think we need it, but might as well pull it up here. So the shape that describes the orbit a planet takes in its path of motion around a star is an ellipse. So the way that you want to word your answer here is that you could say the shape a planet orbits, or the shape that a planet traces out as it orbits around a star, is an elliptical, or an ellipse is the shape of a planet's orbit as it travels around a star. I know at first glance it might seem circular, but it would have to be equal in distance at all point in its orbit if it was circular. So since there is some difference, this little space right here, that means it's elliptical. That's actually the first law of planetary motion, is that planets move around stars in elliptical paths. You will need to know that for your next quiz. Okay, so we're going to press the play button, let the Earth complete so that the second half of its orbit, so that it arrives at the exact same place it began before direction 3 was completed. So let's go back here and allow this planet to complete 1 revolution. Oh, looks like I went over by 1 day. Okay, so jumping back here, use the number of days that has passed, or the number of days that passed minus 1 during this cycle, to state the technical name for this type of motion and state the natural cycle of time that's used to quantify this motion. We want to use number 3 from the pretest to help us answer this question. So number 3, the elliptical movement of Earth around its sun causing the cycle of years, that is a revolution. And it takes 1 year for the Earth to make its revolution around the sun. So a common mistake that people make is they use the word rotation when they're describing the Earth's motion around the sun or the moon's motion around the Earth. You want to get in the habit of using the word revolution. They are different and you will lose a point if you confuse them on your quiz. So I would say it takes 360 days for the Earth to make 1 revolution around the sun, and that is equal to 1 year. So we use years all the time. If you think about, I don't know, I could say I'm 33 years old. What does that mean? It means I've been alive long enough for this revolution, this cycle, to occur 33 times. So that's really what you mean when you say a year. All right, so what cycle is physically occurring 365 times while the Earth is completing its orbit? Let's use number 2 from the pretest to help answer this question. So the movement of the Earth spinning to cause a cycle of night and day, that is a rotation. So there is a difference between these two words. They are not synonyms, even though they are sometimes treated as such. When the Earth spins around itself, it causes the cycle of night and day, whereas when the Earth orbits around the sun, that causes the cycle of a year. So, a day occurs 365 times a year, which is a rotation. And then if you look at this picture, it should be obvious. I mean, if you're on this side of the Earth, it's nighttime. If you're on this side of the Earth, it's daytime. And since the Earth spins around itself 365 times in the time that this takes 1 occurrence, you're facing towards the sun 365 times and away from it 365 times until you get back to where you began in this orbital motion. So, next thing, the universal law just demonstrated by the blue arrows pointing towards each other. Let's use number 9 to help us answer this. Probably don't need the pretest, but you see these 2 arrows right here facing towards each other. Gravity's force, we know that mass has a tendency to attract other mass. And these 2 right here you can see are equal, but we'll get to that in a second. So what did it say, number 9? The law of universal gravitation explains how all massive objects exert forces on other massive objects. Okay, so the next thing, number 5, if the 2 arrows are the same size, look at the strength of the force. Remember, we use the length of an arrow to represent the strength of the force. The strength that the sun is pulling on the Earth is equal to the strength that the Earth is pulling on the sun. You might think that doesn't make sense. Well, remember, forces always come in pairs, and they're equal and opposite. This is bringing us back to October. So the question you have to ask yourself is, why is it that only one of these 2 masses is visibly accelerated? Means its speed or direction is changing continuously. What's the main difference between the mass and the sun? How come the sun isn't orbiting the Earth, but the Earth is orbiting the sun? Well, in this picture, it's not so clear, but it has to do with this over here. The star, or the sun, has a mass that is about 300,000 times greater than the Earth's. So the sun does get pulled by the Earth, but the Earth also gets pulled by the sun. It's just the Earth has much less inertia. And remember, inertia is the property of mass to resist acceleration. So the sun is resisting the acceleration due to the force the Earth exerts on it, and the Earth is resisting the acceleration due to the force the Sun exerts on it, but the Earth resists much less because it's much less massive. I pulled up this fact sheet you can see here. Don't worry about the actual units. What really matters is the ratio. So the Sun's mass divided by the Earth's mass, no matter what units you use, you always have a ratio about 333 times larger. But that's mass. We're not talking about volume here. If we look at volume, the Sun is about 1,000,000 times larger. So you might ask yourself, how come it's 300,000 times more massive, but 1,300,000 times more voluminous? And the reason why is because the Sun has a much lower density. It takes up a lot more space for any given mass. And that's because it's mostly made out of gases and plasma, which is just atoms that have lost their electrons. So just a bunch of charged particles. But that just gives you a little idea about how much more larger the Sun is than the Earth and how much more massive it is. This picture doesn't really do any justice to the difference. A good analogy is that think of the Sun as being like a basketball, and the Earth would look like a grain of sand if you put the two next to each other. Okay, so the main difference between the two objects, why is it that only one gets accelerated? What I would say here is that the Earth has much less inertia than the Sun, which is why the Sun accelerates the Earth. Or you could say the Sun has much more inertia than the Earth, which is why the Earth resists, or I'm sorry, the Sun resists the Earth's acceleration. Okay, so now we want to look at these other arrows. They don't represent forces, but what they represent is, let's see, number 5, the quantity describing how fast something moves along a curved path. This is tangential speed, or what I should have said is tangential velocity. So this red arrow right here, this velocity, this is the tangential velocity. There is two velocities here, but this velocity represents how fast the Earth is moving in this direction at this instant in its orbit. This arrow is continuously pointing in a different direction all throughout its orbit because the Earth's direction is constantly changing as it's being accelerated by the Earth's, or by the Sun's, gravitational force. All right, so where are we here? The red arrow represents, and don't just say the red arrow represents in your answer, just say the Earth has a tangential velocity that's always, I don't know, I guess you would say in a straight line wherever it's at in its orbit. This one is really better with a picture. I'd like to draw real quick. So if I have an orbital path, here's our Sun, here's the Earth. If this is my path, not quite circular but pretty close, a lot easier to draw an ellipse than it is a circle. At this point, well, that's not the line I was trying to draw. Its tangential velocity is here. At this point, the tangential velocity is here. If you just like zoom in on one tiny little part of this circle, you'll see what the tangential velocity is. So however you choose to describe that, don't just say the red arrow represents the tangential velocity, but it represents the velocity or the direction that Earth would be traveling if the Sun just popped out of existence. If we just, boom, took away this, the Earth would continuously travel in this direction, in the direction of the current tangential velocity. I'll come back to this picture in a minute. So we want to press play and observe the direction of the two arrows and the angle the arrows form as the planet completes one full orbit around the star. So the directions of the two arrows, we're talking about the two arrows pointing away from the Earth. So we have the tangential velocity pointing in the direction of, you could say, the Earth's inertia, because remember, inertia makes things not want to change direction. So this is like the inertial direction, and the gravitational direction. So if you look at these two, the entire time this thing was in motion, they were forming a right angle. So the tangential velocity of a planet and the direction of the gravitational force due to the star that it orbits are always going to be at a right angle to each other, no matter where this planet is in its orbital motion. So that's pretty much what you need to say for this one. Or, well, I guess you don't really need to say that, but I did want you to notice it. So what center-seeking motion or center-seeking force is supplied by gravity, which is offset by the inertia of the planet's motion, causing it to move in this third path? So you might be inclined to write gravity, but there's actually a different force that we're talking about, and it's really a combination between gravity and inertia. And we call this, let's go to your pretest, the centripetal force. Oops. So the centripetal force is a force due to the combination of an object's tendency to resist a change in motion, and we can represent that with its tangential velocity, and the tendency of masses to attract each other. It's a shame that this thing fades away, but going back to the picture that I was drawing, if you look at the combination of gravity, so the Earth's getting pulled this way, and it has a tendency to keep moving in this direction. If I was to combine these two forces right here, you would see them pointing in the direction that the Earth is going to end up next. Same thing here. And now obviously it doesn't go in this straight line because this arrow is constantly changing direction, as is this one. So that's why it's a smooth, continuous path. But if we were just take little snapshots and show like the combination of the gravitational acceleration or the gravitational force, which is accelerating it in this path, and the inertial force, or its inertia to keep moving, the combination of these would always bring it in the next, or show you the place that it's headed to next. So you don't really need to draw this picture, but hopefully it's helping you understand. Here's why the Earth ends up in this place next, because the combination of these two things are going to push it or pull it in that direction. Okay, so back to the instructions here. What type of acceleration occurs as the planet changes direction due to the center-seeking force? So this motion that we have here, where the speed isn't really changing, it does change depending on where it's at in its orbit, but when you have a constant change in direction due to the center-seeking force and the object's inertia, we call that centripetal acceleration. So that's the answer to your next question. Centripetal acceleration is the result of the centripetal force. And the centripetal force is due to gravitational attraction and the inertia of mass. All right, so on the right side of the screen, we're going to click and drag the star mass bar to the right and increase the mass of the star to 1.5 times the mass of the sun, and then press the clear button. So here's our sun, increase its mass by 50%. So you should have seen what changed other than the size of this thing, the strength of our gravitational arrows. We're going to hit the reset button. Actually, probably should have told you to check all these boxes. So we're going to press play, Oh, I was supposed to press clear. And observe the planet changing motion as it completes an orbit. Pause the simulation after the planet reaches its starting point on the right side. So I actually just brought that back. Alright, so put this in fast forward so you don't have to wait any longer. Let's let this go through one full orbit. Alright, a little bit too far, probably one day off again. So it was 365, now it's 201. This planet only was able to spin around itself 200 times in its one orbit, whereas before it did it 365 times. So now what we can do is look at how the period, which is the amount of time per cycle, how much time it took for that planet to make one revolution, and how does it relate to the star's mass. So we're going to want to use a complete sentence, a graph, and an expression. So I'll help you with the graph and the expression in my picture over here. But what I want you to do is make sure that you can form the sentence. So what did we do? What did we manipulate? We, as the scientists, changed the mass of the star. So whenever you are making these graphs, you're always going to have what you manipulated on the bottom here. So this is the mass. Actually, let me back that up. The star's mass. So let's pretend like we had three star masses. We had a low star mass, a medium star mass, and a high star mass. And what we were measuring, what we saw there, a change in of, that was a sentence, what we saw a change in of is the orbital period of a planet. Now I could change planet to moon, and I could change star to planet. You get the same thing. Now, let me give this some units here. We'll call this seconds. Oh wait, not seconds. Days per year. It's kind of a weird unit, but how many days happen in 1 year? And the star's mass, this was, we call them solar units. Let me just get rid of these units because it's kind of adding too much to this. Okay, so there are some things that we keep constant here. The main thing that we would want to make sure that we kept constant was our initial distance. But, you know, for now, let's just leave it blank. I don't want to get into too many other variables at the moment. But you always want to write something that's constant here. You talk about the mass of the planet, but since they're so much less massive than their stars, they almost make no difference. What really matters is their average distance. So that's what we should put up here. The average distance is constant. And that's the average distance from the star. Now, that's kind of not true. You can see here, this would offset the average a bunch over here. But there's a fancy word here I really don't want to get into too much, but it would be the major axis, or the distance of the planet in its furthest point from its orbit. So there's just too much stuff that I'm trying to introduce right now. Let's just keep in mind that we want to keep something constant. Okay, so anyways, getting to it. What we saw is as the star's mass increased, what did our orbital period do? The number of days per year, that decreased. So when we have large masses, we're going to get low periods. And we have low masses, we're going to get high periods. And in the middle, you'll get something in the middle. So this right here is an inverse proportionality. So period, we know we've been representing with an uppercase T. It's kind of like time, but it's time per cycle. And we know that this is inversely proportional to mass. So we're talking about a planet's orbital period and the mass of the star that it orbits. We see the larger the mass, the lower the period. So it's moving faster. And there is something that we need to keep constant here, but I don't want to get into major and minor axes. I'm sure you talked about it a little bit when you were learning about ellipses in geometry. Okay, so let's move on to our next question. We just did 9, 10, and 11. You should have said something about as the mass of a star increases, the period of a planet's revolution decreases. We've got a graph and an expression. So what must be increasing if the the distance the planet travels remains the same and the period is decreased? So use number 6 on the pretest. I actually made a little mistake here. This shouldn't say rotational speed, so I apologize. I'm actually reinforcing a misconception that I'm trying to get you to avoid. This should say angular speed. So all of these should have been changed to angular speed. Don't worry about changing it right now. I'm not going to grade you down for my mistake. But what you should be saying is that the angular speed must have increased if the period is decreasing, which just means that something is moving faster. And just the degrees that it travels through around its orbital path are larger. That's why we call it angular. It goes through more angles in a given amount of time, or a larger angle in a given amount of time. All right, so how is this quantity from the last question related to a star's mass? So let's make another graph here. Let's do it over here. So we're going to keep our x-axis the same. Star's mass remains constant, but now we're talking about the angular velocity, not rotational velocity. That would be how quickly the Earth's spinning around itself. So the angular velocity would technically be in radians per second or degrees per second. Let's not worry about that though. And then the constant, we should still always write something. You could say the planet's mass, you could say the major axis, the furthest the planet is in its elliptical path, but I'm going to leave that blank for now. So since the period is going down, the amount of time went down, that must mean that the speed or the angular velocity went up. We know if we have angular velocity is in radians per second. Don't worry about a radian. You can just think about it as a certain number of degrees. If this is going down, then this must be going up. So with large masses, we have large angular velocities, low masses, low angular velocities. And in the middle, you get something in the middle. With no mass, you would have no angular velocity because there wouldn't be any gravitational force moving it in that curved path, making those radians per second occur. Okay, and then is there angular velocity? We'll just stick with the regular v. It's directly proportional to a star's mass. There is actually a fancier one for this. I think it is, I can't even remember the Greek letter right now, but it looks like a W. You can just stick with V sub R. But don't worry about the notation yet. We'll save that for when we get into mathematics later on down the line. Okay, so we just finished half of the simulation here. We're on number 15 now. Moving on. Repeat step 16 and use the red velocities arrow changing length to compare the planet's velocity when it's closer to the star on the left to when it's further on the right. So we want to make the same observation we did last time, but let's pay attention to the length of this red arrow right here. Some of you probably noticed it already last time. So it gets pretty long when this planet is very close, and shorter when the planet is further. So we have a relationship there. The further the planet is from the center of the star, the smaller its tangential velocity is. And the closer the planet is to the center of the star, so I can zoom out here a little, the longer its tangential velocity. Okay, so ready for another graph. Whoops. Okay. Let's get a new layer here. So what we changed, same thing, mass of the star. And what we're looking at now is the tangential velocity of the planet. So this looks just like the angular velocity with a constant something. So this blank space should be filled in when you take your quiz. So low star mass. Oh, you know what? I'm sorry. We didn't have that same y-axis. We were looking at the, not the tangential, or, you know what? I need to erase this whole graph. We weren't looking at how the star's mass changed. We were looking at its distance in its orbital path. So, my fault. The planet's distance. Alright, so as this planet was closer, we're talking about distance to the star that it orbits. As it was close to that star, we had high tangential velocities, and when it was further, it was lower. And in the middle, you get something in the middle. So here's another inverse proportionality. Excuse the terrible line that I just tried to draw. And now it's not drawing anything. Come on. Oh boy. Alright, so it's going to look something like that. So tangential velocity, v sub t, and then we're actually using an r for this, and it should be obvious. We're talking about the radial distance. So if you think about why, it all has to do the force of gravity accelerating it further, so it's going to fly off a lot faster in terms of its inertia is resisting that centripetal force that's pulling inward. And then we would have something constant here, probably the mass of the planet or the mass of the sun wasn't changed when we were looking at its motion around that star. Okay, so that takes care of that. Repeat. Oh wait, no, that takes care of, how's the velocity related to distance? Okay, so repeat step 16. Look at the blue, gravity's arrow, changing length. Compare the strength of gravity as the objects are closer together to when they're further apart. Okay, so it's probably obvious what type of relationship this is. How short those arrows are right now. It's only it's less than 1 grid, and now it's much further. It's like 3.5 grids long. So I have another relationship here that you could be accountable for knowing on your next quiz. What we're talking about is, whoops, okay. Let's say this is really the same variable as last time. I'm going to call it an orbital radius. So how far that planet is in its orbital radius. And this, now we're talking about the strength of gravity. So as we got a lot closer, we saw the strength of gravity was a lot larger. And as it was further, the strength of gravity was much further. So this is just like the last one, but it actually would rise up much quicker and would drop off much faster. It's probably not too obvious in this picture, and this was a terrible picture, but the force of gravity is inversely proportional, not just to the radial distance, but to the square of the radial distance. This should be reminding you of our electrostatics unit, where the force of the electrostatic force was inversely proportional to the square of the radius. This gives you a little insight about how forces work in 2 dimensions of space. It's pretty interesting, the reason why this is the way that it is. I might be able to get into it if I was in class, but it takes some complex drawings. It just has to do with how we live in 3 dimensions of space, and as you move apart from something, things fall off in 2 dimensions as you move away in the 1 dimension. It's really hard for me to draw this and explain it using this software, but you just think about moving away in 1 dimension, you're going to have to account for a drop in 2 dimensions. There's some good pictures in the book, but this little square right here hopefully helps you think about this square right here. Okay, so before I get any more off topic, don't forget you want to include a constant something in these graphs. Just think about what would have to remain constant, and it's usually, if you're talking about distance, it's going to be mass, and if you're talking about changing the mass, it's going to have to be distance. Alright, so that takes care of that one. We got another graph coming up. So we're going to pull the planet to the right 1 grid box further, so the planet starts 3 boxes from the star center, and then press play and pause after it goes through 1 orbit. So let me get this back there, clear that out. We got 1 grid box further, and now we'll let this planet go through 1 cycle. So it should already be obvious, the main change. Still have it in fast forward, keep in mind. So look what happened. It's going to now take 552 Earth days, whereas when it was right here, it was only 200 Earth days. And that's because we had increased the mass of our star to 50% more than the Sun. So what we want to look at is how the orbital period is related to the distance of a planet from the star, or the orbital distance. So let's complete a sentence, draw a graph, and come up with an expression. Alright, so we have our distance from the star, our orbital radius, and we have the orbital period. So we just increased the size of the radius, and we saw an increase in the time that it took to go through one orbit. And we would see the opposite if we did the opposite, if we brought it even closer. So we know this is a direct proportionality. What remained constant was the mass of the star. Might as well write that this time for you. Constant star mass. So our orbital period is directly proportional to our orbital radius. The further away a star is from, or the planet is from its orbiting star, or the star that it orbits, the longer it's going to take. This one's pretty intuitive, meaning you could probably be asked that question without going through this unit and get it correct. We should all know that it takes a lot longer for something to orbit something else if it's much further away. Makes sense. So, further away it is, the longer it's going to take. Okay, we're getting close to the end here. In the upper right hand side of the screen, press the Sun, Earth, and Moon section, which is second down from the top, and then uncheck the gravity, force, and velocity boxes. Alright. Note the initial position of the moon. Press the play button and count the total number of times the moon gets to the same initial position as the Earth completes one full orbit. Alright, so initial position, we're not talking about relative to the sun. We're talking about relative to the Earth. So maybe if I zoom in a little bit. So how many times is it located directly above the Earth? So right now, this wouldn't count as 1. This would count as 0. So let's count it out together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 monthly cycles, 12 cycles of the moon orbiting around the Earth. So take a second to realize that as the Earth is orbiting the sun, the moon is orbiting the Earth. So from the perspective of the sun, both of these things are orbiting it, but you have the moon orbiting the Earth as well, so it makes this kind of cool spiral shaped pattern. Or not spiral shaped, I guess flower shaped. So let's jump back to our questions here. What natural cycle occurs as the moon makes revolutions around the Earth? I would say the moon makes 12 revolutions around the Earth, or around one Earth year. I mean, if I was to ask you a question on the test, how many months are there in a year, it really wouldn't be astronomy. But now you know why there's 12 months in the year, because that's how many trips the moon makes around the Earth as the Earth makes one trip around the sun. Okay, so what solar system model has the sun at the center with objects revolving around it? Let's use number, was it 11? Yeah. So the model of the solar system with the sun at the center is heliocentric. Helio means sun, centric means centered, so the sun-centered model of the solar system. It's relatively recent, like in the last 500 years, that we thought the sun was at the center of our solar system. There was many years, like probably 1,500 to 2,000 years, where we thought just the opposite. Because we saw the sun moving across the sky, we assumed we were the center of the solar system, and at the time the solar system was the universe. So it's just like human beings to think that they're the center of everything, and then science to let us know how little we are. So In the upper right hand corner of the screen, let's click on the Earth and Moon section, which is the third one down from the top, and press play after it completes one orbit. Okay, right on. 28 Earth days for the Moon to make one trip around the Earth. So, how many days does it take for the Moon's revolution? 28 Earth days for the Moon to revolve around the Earth. And how many weeks pass in this time? Well, we know that there's 7 days in a week. You divide 7 into 28 and we get 4 weeks in a month. Something else I wanted you folks to point out here. Take a look at what the Earth is doing. It's not quite still. It's moving a little bit. And that's due to the gravitational force that the Moon exerts on the Earth. The ratio between these two is much closer. I believe it's 1 to 6. There's about 6 times more mass in the Earth than there is in the Moon. Whereas when we were talking about the Sun, it was 300,000. So pretty big difference there. That's why we can see the Earth kind of bobbling around a little bit due to the Moon's revolution and its gravitational force, causing it to accelerate. Okay, so, did I just answer that question? Yeah. So press play and observe the behavior of the Earth. Like I was saying, it jiggles around a little bit. Why is this behavior observed when the moon revolves around the Earth, but not as the Earth revolves around the Sun? Well, the main difference is the Sun and the Earth are much closer in mass than the Sun. The Moon and the Earth are much closer in mass than the Sun and the Earth. So that's the reason why there's visible gravitational, I guess you could say, jiggling. So we're going to click the off button in the gravity section of the box in the upper right and observe the motion of the Moon after there's no attractive force keeping it in orbit around the Earth. So what would happen to the Moon if we just turned gravity off? It would just fly off, as Earth would fly off away from the Sun. So, can we get that thing back here? Guess not. Oh, here we go. So, describe the motion of the Moon after gravity turns off. Be specific about the direction. I think the main thing that you want to say is, if gravity isn't on, objects are going to move in a straight line unless an outside force exerts an attraction on them. I mean, if I keep gravity off, no matter where I put this Moon, it's just going to move in a straight line unless I jam it into the Earth. So, I would say here, not necessarily the Moon, but just unless gravity is accelerating objects, they move in straight lines. Okay, so I forgot to open up this link in advance, but it won't take long for me to get there. This is kind of a cool simulation. You should play around with this a bit if you get a chance. In the upper right side, select the preset drop-down menu, click on the Sun, the Moon, and the Comet setting, and then press play and observe the motion of the two bodies. So Sun, Moon, and Comet. I must have meant Sun, Planet, and Comet. I said Sun, Moon, and Comet. Is that an option? No, this is fine. Okay, so we are going to observe the motion of these bodies. So this blue part right here, this is the Moon. I'm sorry, the pink part, that's a planet. And then what that was before, that was a comet. So the main thing that I want you to notice here is the difference. How is the orbit of the asteroid different from the orbit of the planet? Well, there's a quantity known as eccentricity. You don't really need to know that, but I do want you to get an idea about how comets move differently than planets. Planets are much more closer to a circle, whereas comets have a much more elliptical orbit, meaning they get very close and they get very far away. And planets, they get closer at some times and further away at others, but it's not as dramatic of a change as it is for comets. So hopefully you play around with this a little bit. There's a lot of cool shapes that get made when you take a bunch of masses and get them close enough to each other. This simulation was made all using the laws of physics, so there's no, I don't know, I guess fancy tricks that they put in here other than just the equations that are used to describe reality. And as you can see, eventually order turns into disorder. I guess the next thing that we talk about, the initial settings for one of the presets, find out how difficult it is to create a system with stability, which means it maintains regularity and predictability. So it does the same thing over and over again, which allows you to predict what it's going to do. So what we should have seen is that eventually regularity and predictability goes out the window. You could say that all organized systems eventually become chaotic. That's definitely not something that's going to be on the test, but it is an interesting fact about the universe. No matter how concerted and organized things seem to be, they will eventually unravel and turn into a chaotic situation. Okay, so that concludes this simulation, and it's the last one of the year. Hopefully you've enjoyed these, probably more than the videos of them.